All right, good morning. My name is Mallar Chakravarty, and I'm a assistant professor in the Department of Psychiatry at McGill, and my lab's located out at the Douglas Hospital, which is the psychiatric hospital associated with McGill University. And what I'm going to try to sell you on today is the idea of modern neuroscience kind of being this incredible multidisciplinary space, which really needs people like you to come and join and help what we're doing. So a lot of the work that we're doing right now involves multivariate statistics, machine learning, that kind of thing. My own background, just to talk about my own personal journey a bit, was doing an electrical engineering degree in at the University of Waterloo, very mediocrely. And when I did it, I went through the co-op program there, only to find out I really didn't like being an engineer that much. And I did a lot of work terms, and I also found out that every work term, we had 6 in total, kind of, for me at least, followed a very similar pattern, is that I'd go to work for the first month, I'd be very excited, and then I'd be somewhat bored by the 4th month. Not to turn you off working, because I know there's a lot of people here looking to recruit you, and I'm sure their jobs are amazing. But I'm going to try to sell you on the fact that academia is also amazing, and it's a place where you can play and create a sandbox that is your own. And it's a really multidisciplinary space. So I'm going to introduce you, before I do talk about any science and the type of things that we do, I'm going to talk a little bit about my team. And this is really important, because more and more, I think modern neuroscience is really adopting a physics model, in the sense that big projects are really are out to be solved by a large group of people, and that no one lab, no one group can really solve the complexity of neural dynamics, how brains develop, how brains age, how diseases onset by themselves, and you need this kind of multidisciplinary aspect. So in my lab, I'm cross-appointed in 3 departments, potentially 4 soon. One is the Department of Psychiatry, the other is Biomedical Engineering, and the last one is Institute of Integrated Program in Neuroscience, sorry. So I tend to kind of pull students from both neuroscience and engineering pretty equally. So just to give you a sense of where some of my students come from, so right here, it's missing Gabriel Devigny, who's often at this retreat, but he couldn't make it this year because he just had a kid. But he's kind of my right-hand person in the lab, and he did a PhD in material physics. Other people in the lab, Sashi over here, who's eating my son's shoe, did a BA in psychology, a BA, not a BSc, a BA in psychology, and has recently performed one of the biggest meta-analyses on autism neuroimaging data ever done, learning how to do tons of image processing, statistical analysis, and doing this in collaboration with other members of my team. Lonnie Kupo over here did a joint major in theater and neuroscience at Occidental College in LA, and has brought a lot of really, is a really dynamic individual, and is a really, and is beginning her PhD in neuroscience and looking at the effects of cannabis on the developing brain. And Rayan Patel over here is working on multivariate statistics to look at multimodal integration of data to understand how the brain ages over time. So this just gives you a sense. The last person I'll talk about is Charles Legasse over here, actually. And Charles is a guy who I think really typifies a lot of modern neuroscience students. He comes with this incredible background in knowledge and coding. He's been working on machine learning projects in my lab, most related to image processing and image analysis right now, and so very highly theoretical questions. But in general, his background isn't necessarily in computer science. His background, he's doing a major in neuroscience with a minor in computer science. So this often kind of is really typical of the type of students that kind of get drawn to my lab. The gentleman down here is Nikhil Bhagwat, and his work is the work that I'm going to be highlighting today. And he just finished a PhD in my lab, and did some really interesting and almost interesting work in how to use machine learning in combination with multiple streams of data in order to use it as a healthcare prognostic or diagnostic tool. And so there's a lot of questions out there right now about how machine learning and artificial intelligence whatever you want to call it, will be used in the healthcare field. And I think there's a lot of reticence by doctors, for example, to give up their paycheck and hand it over to a machine that's crunching through data in the background. And there's also a lot of reticence by the general public to, maybe not the people in this room, but certainly older individuals who don't really understand what's happening, to give up their personal information to a cloud to have it crunch through probabilities to tell you you're at risk for Alzheimer's disease, right? So what's likely going to happen, and the way a lot of insurance companies are moving towards, or the way a lot of healthcare providers are moving to, are some combination of the two. So really kind of introducing artificial intelligence into healthcare as a doctor's assistant, if you will, that maybe where the artificial intelligence can see patterns that obviously a doctor can't, and can remember things obviously a doctor can't, but the doctor finally has the final stamp and is the person who delivers the information to the patient. And so one of the big major foci of my lab is examining Alzheimer's disease. So typically we've done this through the lens of neuroanatomy, using MRI imaging, sometimes brain function as well. And we do a lot of things in my lab where we kind of bridge between clinical populations and basic neuroscientific questions using animal models, right? So and part of what we want to do is try to understand kind of signatures that we see in humans, in animals, and see unintended observations that we see in animals, and try to kind of validate those in humans. This talk's not going to be about that. This talk's going to be more about kind of this prognostic application that Nikhil built at the latter end of his PhD. And so by now you guys have all heard the alarmist views about Alzheimer's disease in the newspaper. Seemingly there's a new article almost every day about how we're all doomed, the world is too old, healthcare systems are going to buckle under the pressure of Alzheimer's disease. And by and large, this is true. By and large, this is kind of one of these healthcare problems that we've seen, kind of like environmental issues, that we've seen coming for decades, and we've just really haven't figured out how to do it. And a big problem in this field is that we kind of treat brain disorders in the way we treat cardiovascular disorders, in the way we treat broken legs, and the way we treat broken noses. There's no cast for an aging brain. There's no stent that you can put into a valve. If you consider the fact, we've made all these miraculous discoveries, and so in cardiovascular disease, for example, 50 years ago, having a blocked artery, cardiac artery would have killed you, right? 20 years ago, they started putting in stents, which is basically just you fish a wire through someone's artery, and you fish it close to the heart, and you expand balloon, and you basically leave a bridge in there that opens up a blocked artery. The recovery time on that 20 years ago was about a week, 2 weeks maybe, requiring some hospitalization, especially if you went through an artery that was in the thigh. My mother just went through this procedure on Christmas Eve this year. She was out of the hospital in 3 hours. So the question is, what technologies can we bring to bear on neuroscientific problems, on neuropsychiatric problems that can have that kind of impact, right? But the fact of the matter is we don't understand enough about the brain to have a stent. We don't understand enough about the brain to have a cast, right? To have that 2-hour fix. And we've been treating this problem that way for a very long time. So what this slide is here to show you is to basically show you what the prevalence of Alzheimer's disease will be in Canada between now and 2038. And you see this rising prevalence in the middle line, in the black line across both genders, or both biological sexes, showing that basically we're going to have a tripling in the number of Alzheimer's cases in Canada in the next 3 years. And this is 1.2 million people who have no treatment. So Alzheimer's disease is defined as the loss of memory and cognitive function leading to functional impairment. And functional impairment means disability in your actions of daily living. And so what those actions might be would be bathing, eating. So when people die from Alzheimer's disease, quote unquote, what happens is they don't die from the pathology in their brain. They die because they forget to eat. They die because they leave a pan on the stove for too long and the house burns down. So that's how one dies from Alzheimer's disease. So by and large, the thinking, so just to give you a little more background, it's caused by this kind of gunk that, the technical term is gunk, that accumulates throughout the brain, particularly between neurons. And these basically these misfolded proteins that aggregate where synapses connect and talk to each other, and it impairs the synaptic connection, leading to neuronal dysfunction at the single neuron level, and then downstream there's kind of this network propagation where neurons die throughout the brain based on where these kind of misfolded proteins aggregate in the brain. And so this is just kind of the cartoon example of a normal brain versus an Alzheimer's disease brain, but in reality things are far more complex than this. Some Alzheimer's brains look strikingly like normal brains. Some normal brains look slightly like Alzheimer's brains, right? So there's this vast heterogeneity in the clinical presentation and in the phenotypic presentation of these people who may or may not have Alzheimer's disease. So like I said, there's no cure, but there's a huge socioeconomic cost and burden. So we're looking at 1.1 million Canadians impacted currently, and a 10.4 billion per year healthcare costs for treatment and management. And that doesn't include health care provided and days lost from work by family, by siblings, by partners, by daughters and sons. And so so what's been happening now in the Alzheimer's field is that more and more drug companies are pulling out of that field. There is no magic pill. There is no panacea. There's nothing that's going to, there may be a few things that delay the disease, but by and large, there's nothing that works, and drug companies don't find this profitable. Turns out, your brain acts like most major organs in your body, and it likes things like exercise and good food and socialization. And so more and more, all new trials are not geared towards treatment, but they're geared towards prevention. And prevention happens 20 years before the onset of the disorder. But the problem is, 20 years before the onset of the disorder, you have no idea who's going to have Alzheimer's disease and who's not going to have Alzheimer's disease. And so this is where Nikhil's work is becoming very instrumental. So the question is, can we make prognostic predictions a few years or several years prior to potential Alzheimer's disease onset? And so the idea, like I mentioned before, is to kind of bring back this idea of continuous monitoring for a doctor's assistant. So if you have any one patient, you can imagine that a doctor will bring them into the office, perform some cognitive tests, ask some questions of the patient's family, and ask, is this patient likely to be stable in the next 5 years or decline? And decline towards this Alzheimer's path, right? Generally, what ends up happening is that people with mild cognitive impairment, which is this kind of in-between phase before the onset of Alzheimer's disease, have a bunch of symptoms that look like depression. And so those symptoms look like lack of motivation because they're starting to lose function and kind of lack of caring. And so what ends up happening is they're seen by their GP as a geriatric depression case and given the wrong drugs, and they stay there too long. And then by the time they get to a hospital, they have a full-blown case of Alzheimer's disease or Alzheimer's disease dementia, right? So if we could find those people 5-6 years before the onset of disease, we could do a lot. It's been shown time and time again through exercise trials, through diet trials, that we can delay the onset of the disease by 5 to 10 years if we do the right things at the right time. Other biomarkers that are typically used, like hippocampal volume. So hippocampus is the main memory center of the brain. We know that it degenerates through time, and that's a very clear univariate path that you can take. You know, if you take just Gaussian statistics and model that in any which way, it's a pretty clear indicator of Alzheimer's disease. But by and large, these are the actual trajectories and how they correlate with functioning, right? And this is just an Alzheimer's scale on the y-axis and a hippocampal volume for a bunch of subjects on the x-axis, taken over about 1,000 subjects over time with multiple time points of data. And if I kind of draw your attention to, say, when that black line above the 3,000 mark, you can see that the hippocampal volume goes all over the place, or the cognitive profile of that individual goes all over the place over time, right? So it's not the most robust biomarker that we have out there. But what we do know is that demographics make a difference, genetics make a difference. So there's one genotype known as ApoE, where if you carry this specific variant of ApoE, your odds for having Alzheimer's goes up by 20 to 40%. It's not a guarantee, but your risk moves up. If you carry two variants, you gain another 20-40% of risk. You're almost guaranteed to have the disorder at some point in your life. We know that MR images can provide some vital information towards this. So the idea is that could we take a bunch of individuals at their baseline assessment and then maybe with certainty stream a few of them into this stable or decline phase and maybe do a little better, the next time they come back, or the next time they come back, right? And or ask them to come back a couple of months later and then say, can we improve the certainty of our prediction after we ask them to come back in 6 months or 12 months or something like that. And in the interest of time, I'm gonna move forward. And so what Nikhil did is he basically wants to created this algorithm that projects and considers this stable or declined phenotype. And we use machine learning, and I don't have to tell this room that machine learning has tons of applications in healthcare. For image segmentation, more and more, it's being used, and we're trying to pull that together in my lab for mental health diagnostics and skin cancer detection and so on. And so we use a huge database of publicly available data from this group called the Alzheimer's Disease Neuroimaging Initiative. And the first thing we did is we looked at these 69 subjects who had anywhere about 7 time points worth of data over the course of 9 years, which is a phenomenal data set that not a lot of people have. And in just a very simple way, we said, can we model trajectories of cognitive stability and cognitive decline? We didn't think about diagnostic conversion. What we were interested in are slopes, right? You want to know who's flat and who's moving down. And so for this, we used a typical Alzheimer's disease scale, which is called the Mini-Mental State Exam, which is used in a lot of clinics. And we just did a hierarchical clustering analysis. And what you find is that you can segregate your groups into stable, which is up here in the blue, and decline really, really nicely. And so then what we wanted to do is use that as our template. And basically we wanted to ask the question, for people who have less data than those 7 time points, can we a priori classify them into one of these template classes in our training and testing? And then for new data, can we then use that as our gold standard, and for new data, classify these individuals as stable or decliners in the rest of what we do? And the way we did this is we used this idea that Nikhil has cleverly labeled the longitudinal Siamese network. The Siamese network's used a lot in facial recognition and image recognition problems. And so if you have 2 images of the same person, you can ask the question, does this person look like the same person, or is the distance that you're embedding very, very far away? And so you can use that embedding as something that, if you have 2 time points worth of data, of MRI data from the same person, you can ask the question, how far apart is this person getting from himself? And so if you have these declines, you can get this distance between MRI images that you see here on the right. We then modulated this distance using that genetic feature that I told you about. So basically we know that that distance between individuals is going to get greater if you have if you're an ApoE4 carrier versus not an ApoE4 carrier. And then we concatenate that with clinical scores to predict the final outcome on a subject level. So basically what we're able to do now is then ask the question, are individuals in the next 5, 6, 7 years likely to decline towards Alzheimer's disease or not? And even if you have a patient with Alzheimer's disease, some of them actually do stay stable. And it's very valuable to find out, regardless of diagnosis, if they're on this kind of downward trajectory or not. We did the typical thing where we compared this work with a lot of the standard algorithms that are used, and our work is here in the black. Is my mouse showing up there? Yes, it is. Over in the black, and we do in accuracy and AUC and the confusion matrix, we do very well compared to these other methods. We also then looked at the generalizability of this method by applying it to another data set. So there's an Australian version of this kind of data collection that's out there and that exists, and called the ABLE. Australian Imaging and Biomarker Lifestyle Assessment. And by and large, we do quite well when we do that as well. So what we've done is we've created something that we can then use for prediction, we can port to other databases, and now we're actually looking to see how we can use this in a prospective manner. So we have about 400 people we've recruited already, we've seen at one time point, and now I want to predict what class they're going to be in before we even call them back, and make that our categoric labeling for those individuals. And that's kind of where we're going. And by and large, what hasn't happened in this field, in this domain, this kind of integration of artificial intelligence and healthcare and neuroimaging, is this kind of prospective application towards seeing, can we predict the future without even seeing these individuals? This is nice that it works on data that's already collected, but it's not great that we can't use it in any other way. So just a quick summary and my conclusions. We use this directly modeling technique where we can create data-driven definitions of symptomatic progressions at the individual subject level. What's nice about this, and I didn't really talk about this much, is that this technique has the ability to handle missing time points. So although we created this trajectory over this kind of 70 individual group of people, we kind of use distance measures to figure out where each individual should land within this trajectory kind of landscape. And so it also highlights the importance of periodic monitoring and figures out who should be monitored periodically. It handles multimodal and longitudinal data quite nicely, and we did a lot of replication on a lot of data sets. So with that, I'm going to conclude my talk. I'm going to say thanks to my team, and if there's, can I take questions now? Because I might have to leave quite early, so if you have questions now, I'd be happy to take them at the moment. Yeah.
Hello?
Yeah.
So I haven't had time to really word out the question properly, but during the work that you guys have done with the machine learning to sort of help predict the trajectory of the stability and decline, are there any cool or are there any sort of insights that you've gained? Because earlier you mentioned that there's different factors like demographic and diet and exercise, like lifestyle. Are there any things that you've realized through the use of the AI?
So right now we've only done it for this kind of subject level classification. We haven't gone the other way where we've looked at either in a univariate way the data that drives it. We've done a couple of things where we see, just geriatric depression, which is a huge risk factor for Alzheimer's, isn't terribly different. This data set, the problem when you use public data is you're using public data and you only have what they give you. So I'd love to know about smoking or BMI or things like that could have a really interesting, but those are actually tough to glean. There's a newer version of this data set that's been cleaned up that we're going to go back and look at, but we haven't had a chance yet.
Thank you very much. You had a great talk, by the way.
Thank you.
Just a quick question. You said earlier that I think I understand from what you said that if somebody is to have more socialization and if they do have a healthier lifestyle, they eat better food, they sleep properly, they exercise, that it's a better way to push Alzheimer's further, right?
Yeah.
If that's a solution, wouldn't it be easier to push that everybody should in that case do it, and then even whether you have Alzheimer later on or not have Alzheimer later on, you're still gonna gain either way.
Yeah. Yes.
Health-wise. So I thought, wouldn't that be a better approach?
Yeah, but
everybody's covered.
I 100% agree. Do you know how many nutrition or exercise physiology classes your doctor takes?
A lot, probably.
0.
Oh. Okay, wishful thinking.
So that's why, right? That's not the training. The training in medicine is to deal with the symptoms that you see before you and not to think, ahead of time, right? So in cardiovascular disease, we've done better with that. So we know that blood pressure is a great indicator of future cardiac problems, right? Cholesterol is a great indicator of future cardiac problems. Turns out a lot of those things are true for Alzheimer's disease, for example, as well, except we haven't gotten there in terms of bringing that into the clinic. And I think part of the problem is that the proximity to the disease can be, we know that pathological accumulation happens 15, 20, 30 years before the disease ever comes off. I'll give you another anecdote. There's a very rare variant of Alzheimer's disease, which is a familial variant, which means that if you have this one genotype, which I didn't talk about here, you're guaranteed to have the disorder. 99% chance of having the disorder. In studying people who have that gene, if you look at the people who walk more than 200 minutes a week versus those who don't, their age of onset is 10 years later. So they push off Alzheimer's disease 10 years later than the others. So it's a difference of having it at 45 or 50 versus 60 or 65. But I agree with you. Yes, that's
Everybody
what
should try to be healthy.
It's not rocket science or neurosurgery for that matter. Yeah.
Hi.
Hi.
You were talking about your databases earlier about the statistics about the brain over a period of time. I was wondering, how do you decide what data is actually relevant to Alzheimer's? Or in the future, would there be data that you would like to have that wasn't recorded in the past? And
one thing I failed to mention, which I think is really critical, is that people are trying to do stuff like this, but with, I mean, the idea would be to push this into the clinic, right? That'd be the next best step. The problem with clinical data is that every doctor, every nurse has a different definition for the same thing, right? And so handwritten notes, or even, if there are different options that roughly mean the same things, some doctors will go down and find the right one. Some doctors will go and find the one that's closest on the checklist. So I think there's this, and companies that have approached me about this technology, basically what we end up coming to the solution of is that actually we just need to clean up data for the next 3 years before we actually apply this. Medical records are horrid and ugly places. And so I think that actually is the next big boom to happen in this kind of subdomain, is how to clean up medical records so we can actually apply methods, not this one necessarily, but like this, to do this type of work.